So it went down the message was,
All good? Okay. Good morning. Welcome, everybody. Is this too loud? Or it's okay? All right. So welcome to our September meeting of Morris Museum Astronomical Society. Thank you all for finding your way to the library. I know this is a change for us, but I appreciate you all being here. We took a break over the summer and we have an exciting fall schedule that I'll quickly share, but it's also available over there and on our website. So today we have Before Pluto Was Pluto, an accidental capture by Dr. DiMario. And I'll do a bit more of an introduction right before we start. On October 11th, we have Lost and Found, Astronomical Oopsies by Lonnie Eunice. And on Saturday, November 8th, back here at the Morris County Library, we have James Webb Space Telescope Update, 3 years of images with Walt Windisch. We also have been very busy over the summer, though we took a break from programming. We've been very busy over the summer with outreach events across various libraries, and we have 4 more outreach events coming up. They're at Glen Ridge Free Public Library on Monday, September 29th, Scotch Plains Public Library, October 16th. That was a reschedule from this week due to weather. New Providence Memorial Library on October 27th, and Warren County Library Northeast Branch on November 10th. So we have an exciting fall. We hope you guys will all continue to come and encourage and invite others. So without further ado, I'd like to introduce our speaker today, Dr. Mike DiMario. Dr. DiMario has recently retired from Lockheed Martin, serving various executive roles, and has held executive engineering positions at General Electric Medical and Lucent Bell Laboratories. With regard to his astronomical pursuits, he chairs the Amateur Astronomers Association of Princeton Astro Imaging Group and spends many a night astro imaging and does considerable astronomical history research. He co-shares the earliest precovery of Pluto on photographic glass plates located at Yerkes Observatory. So without further ado, welcome Dr. DiMario, Before Pluto Was Pluto.
Thank you very much. Let's see if I can get out of this loop. And then
Bye-bye.
over the presentation. All right, is it good? All right. So I also have some notes here, so I'll be just a couple of points I don't forget. First of all, I want to thank the Astronomical Society for inviting me to give this talk. I also want to thank Yerkes staff providing the actual loop slides that you saw when you were coming in. That was provided by Yerkes. So they're always very happy and very excited when I talk about Yerkes. And so a lot going on at Yerkes. So on the, I have to remember how to advance this. All right, so on the agenda, I'm talking about a brief history of Yerkes and the amount of revitalization it's actually gone through. It's gone through 2 revitalizations, actually. And can't talk about Pluto and Pluto recovery without covering a little bit about the history of Yerkes. Talk about Pluto, brief history of Pluto itself and its characteristics. And a lot was learned about Pluto as a New Horizons spacecraft zoom past Pluto. And then talk about Pluto precovery in 1909. Now, what is a precovery? A precovery is a...
Ask to be a little bit louder.
Okay.
We can turn this up. Okay, go ahead.
So precovery is stands for pre-discovery recovery. Basically, it's a process of finding an image of an object that was already discovered on old photographic plates. So precovery is really only used in astronomy and a fairly new word. Okay, the history of Yerkes was actually really started at the Chicago World's Fair, and Yerkes himself coined it as the birthplace of modern astrophysics, and he's one of the first people actually to publicly use that word at that time, astrophysics. Like, what is astrophysics? But the Chicago World's Fair, known as the Columbia Exposition, was the first time that people actually saw the plans for Yerkes, plus the telescope itself, without the lenses, was actually at the Chicago World's Fair. The tube and parts of the mount were actually at the fair. Picture here is March 9th, 96. It's taken by Richard Dreiser, one of the staff members, Comet Hayataki. This is looking north. Of course, the Great Dome and the comet. Nice. It's a nice shot. Just a quick picture of Yerkes itself. This is the front. Of course, the large dome, two smaller domes, and of course, there's a mini me there. Originally meant for amateur astronomy, you know, put like a C10 or a meet in there. I don't think there's still anything in there. Last time I looked, there was actually a lawnmower sitting. Lawnmower actually was in there, but that's the building itself. So where is Yerkes? Yerkes is just on the north side of Lake Geneva. Here's Chicago, Milwaukee, and Madison, Wisconsin. So it's really the playground for people out of Chicago in the summer. Great lake, great deal of boating on Lake Geneva. People from Milwaukee really don't go to Lake Geneva; they just go north. But that's where Yerkes is. And of course, the winters get pretty bad there, which I'll talk about in a little bit. But so that's where Yerkes is. Another shot of Yerkes, great sky. Sky doesn't always look like that, of course. Prone to see that type of sky in the winter, not so much in the summer. Another shot of Yerkes. The property itself is 50 acres. It was originally 53 acres when it was originally purchased by Yerkes. It was 50 acres now. 3 acres was actually sold to a small business. But it's a gorgeous property. It was originally designed by Frederick Olmsted, who actually did the New York Central Park, did the landscape architecture for New York Central Park, as well as the University of Chicago campus and several areas of the U.S. Capitol. So he's the one that actually did the landscape design, probably because he already did University of Chicago, and so that's just a natural thing for him to do at Yerkes. A lot of the pictures show the 13-foot slit open like that, facing this way. As many of you know, when you park a telescope in the parking position, that's sort of the parking position for the dome as well as the 40-inch refractor. So that's why a lot of pictures show it like that. They keep the dome open just for heat, just for cooling. Of course, you do get birds in. You know, not as big of a problem as you might think. Of course, they've renovated a little bit, and now it's solar cells on the roof, which is fairly recent. There's another picture of the large dome. It's 13 feet wide, and this is the main front entrance. This is the front entrance. So Yerkes University, Yerkes Observatory, University of Chicago. That likely will not change, even though University of Chicago no longer owns Yerkes, but for historical reasons, it's probably most likely will stay. Obviously an older photograph before there were solar cells. And before the dome was actually refurbished. But winter, to get from one dome to another, it was always quicker to go across the roof. Because otherwise you go through all the hallways, up the helical stairs, just to get a piece of equipment from one dome to another, which took like 25 minutes. Quicker just to go out one dome, cut across the roof and get into the other. The building has great deal of what's called grotesque architecture. In this particular case, that's Yerkes. Not always, they're not always very flattering renditions, but you know that's what Yerkes look like. So at least they got a good portion of the mustache. But the building, the entire building has this type of relief. It's really remarkable the amount of detail that the building itself has. A little bit about Yerkes himself. He was he owned 3/4 of the L system in Chicago. He actually designed it and had designed and actually owned 3/4 of it. He also did the Underground Railroad system in London. So he had a great deal of money, and that's why he financed Yerkes, because he was interested in philanthropic activities, because he had a very poor reputation in business as well as personal life, and he felt that he had to do this in order for a redeeming quality. But so that's why he. So actually, it's William Harper, who was the founder of University of Chicago, and George Hale actually approached Yerkes for the actual funding of Yerkes, because they found that there were 2 large glass plates, pieces of glass that were in a warehouse that had to be used. Otherwise, they were going to go to Mount Wilson in California, and that's what they were originally destined for. And because they couldn't get the land at Mount Wilson, these glass plates, this glass sat. Hale and Harper jumped on the opportunity to get this glass. And so Yerkes said, well, I'll fund that. And originally they just wanted to use it to observe the sun. And Yerkes said, no, I want more than the sun. I want everything. And so that's how that's what happened. Otherwise, Mount Wilson would have ended up to have the largest refractor in the world. It wasn't for that opportunity that they just jumped onto in order to get that glass. Here's a picture of the refractor. 2 different types of pictures, but you can see the immensity of it, the actual amount, and the size of the scope. Here's an observer. Another picture, first large star up there, maybe a Vega or some other bright. So this is how it looks at night within the dome. There's a reddish hue, of course, but certainly not dark. However, in the winter, it is cold. It is very, very cold. So, and we'll talk about that. There's also these large wheels. I don't know how well you can see them. There's actually 36 of these wheels, and they're 30-inch. They are 36 inches in diameter. So that's the number of wheels that actually rotate this dome around. They are the original wheels, and they're still fully operational today. Okay, the first revitalization. It started to decline in 1904, and the reason why it started to decline is because Hale went to Mount Wilson. Hale actually was the first director and actually started the actual building construction of Mount Wilson, thus leaving Yerkes. So at that point, a lot of the astronomers started leaving. They followed Hale out to California. What also happened was the weather was better. Why should I freeze in Wisconsin and have these cloudy nights when I go to California, right? So that was another thing that happened. Except in the summertime, they actually came back. Barnard would go back and forth, and they would actually work at Yerkes in the summer. Then Otto Struve then came in. He got his PhD in 1923 at University of Chicago. And so he came in and resurrected Yerkes, recruited a great deal of elite astrophysicists as well as optical designers. Of course, when Hale left, lack of funding, support, but Otto Struve came in and resurrected it. Okay, the second revitalization started declining in 2005. And University of Chicago, because of the weather and because of the larger scopes being built in Chile, the use out west, the amount of research grants and research money flowing to Yerkes was really diminishing. And so U of C was looking to actually sell Yerkes, the observatory, and the property. And at that time, there was strong lobbying going on from commercial real estate developers to actually build condominiums and a large golf course, which would have been quite a sight on top, looking over like Geneva, golf course, condos, great deal of money. The sale did not materialize, and the reason why it didn't materialize is because the local population, the locals were dead set against it. They didn't want Yerkes destroyed. They didn't want a golf course. They didn't want condos, which actually, when you think about it, it's like, why wouldn't they? Because it means employment, it means revenue. You know, the Chicago people would love to come up. But the flip side of that was they're already here. The lake is already crowded, right? So it was felt that the people actually lived in Lake Geneva, they were already at their max, and they didn't want more of it. And so they didn't want to lose Yerkes, and so they actually fought against this development. Then UFC had then announced in March 2018, that they're going to cease operations October 1st. Then they went dormant. So Mike Key would no longer work at Yerkes. They actually changed the locks and they shut the place down, except for the plate vault. The plate vault holds over 180,000 glass photographic plates. It is a world treasure. This is one of the few in the world that holds as much glass plates, other than Harvard. And UFC wanted to began to digitize the plates. And one of the reasons why they chose to start digitizing the plates is because of the work that we did on Pluto. They realized that the plates were a gold mine. But the goal was to find comets, on the glass plates. And so obviously you need to prioritize 180,000 plates. But so they started this digitizing, and they kept working on in the glass plate vault. Although a lot of them were being destroyed, these are 1900 glass, around 1900 type plates. They have emulsion film on them. Emulsion dries out and cracks, peels off. As well as that they were all in big aluminum cabinets. You imagine 100 glass plates lined up vertically. Well, what happens to the ends of these glass plates all lined up, right? If they lean, the end plates crack and break. You went through it. If you look at every shelf in the cabinets, that was the condition of what was occurring. All the ends, they're all broken. Of course, you never know what was that, what kind of data information were run broken place.
Yeah, Mike, were they doing spectroscopy like they were doing in Harvard or just astronomy? What were they using place for?
They weren't. They were just housed there. No, they just sat there. In fact, we were one of the first ones that actually went in there and started looking, you know, what can we glean out of these plates? And then someone at UFC finally woke up and said, wait a minute, you know, here we it becomes a whole other story, right? Bunch of amateurs are coming in, if you will, and they're changing how we think about all this, right? And so that's why they decided we need to do something. Albeit they still had the problem of all this property and Yerkes is sitting there and great deal of money was to be had, right? So a bit of a conflict. All right, so the Yerkes Future Foundation was formed, which is a nonprofit organization. They were able to acquire it May 1st of 2020. Dennis Coy, who is a current director, he was a director of a few museums, so he had a great deal of experience in resurrecting and running museums. So he became the director. Campaign was to raise $25 million. They're currently up to 32 million now. And the goal is 74 million by 2033. And they started tours, so they actually opened on May 27th. And they're offering tours. They host weddings now, art fairs. So it's not just strictly astronomy. That in the daytime they have many other activities that are occurring. And it's become a destination spot. Amanda Bauer now is the director for head science and education. She joined in July of 22. She was a deputy director of the Vera C. Rubin Observatory, which just went online in Chile. So she actually chose to go to the Yerkes and leave Rubin for this opportunity. Just another few takes of the refractor. So it is a doublet F19. There's Beesbrock, famous astronomer. You can tell the objectives hasn't changed much except for the protection around the objective. Cudworth was the second last director. This is the business end of the 40-inch instrumentation. All that can be pulled out and reused and reconfigured. This is the original 40-inch control panel, still operative today. However, it's not used very much because all the controls are now on the business end, but that desk is still there. This I took during refurbishment. They actually covered it as they cleaned the inside of the dome. They covered the mount and the reascension and declination gears. As I said, it's on the north side of Lake Geneva. It's it was 1895. It's on 53 acres. It's now 50. As I mentioned already, the dome rotates on 36-inch wheels. And of course, the observing slit is 13 feet. The other two domes, they're about 30 feet in diameter. And at that time, in 1897, the northeast dome, which is this dome here, housed a 12-inch, and this one had a 24-inch Richie Creighton, scope in it. Hale had his own private scope in his backyard in Chicago. He wanted to actually put a 16-inch in, but I think that actually happened, but you can see the dome from Lake Geneva. Of course, here's the lake. So you can tell the property, the property is very, very prime. A picture of the Great Dome construction in 1896. All right, this is the entrance into Yerkes. The front door is here. And what's interesting, when my wife Linda and I were there, or shortly after they reopened, I was like, why does it look so different? And the reason why is because it's no longer yellow. This is all marble. Everything's marble. And over 100 years of use, cigar smoking, cigarettes, pipes, the smoke made the walls and the floor, the ceiling was all this yellowish green. They went in and scrubbed it all down. They got rid of it. And all of a sudden the marble had color. Like I never knew the floor was reddish. Right? I mean, it was really quite remarkable. Also, if you ever seen the movie Chain Reaction, 1996 action movie, with Keanu Reeves and Morgan Freeman, there's actually a chase scene, comes in, goes up the stairs, go up these stairs leads to the 40-inch refractor. So the movie depicts this chase scene on the Yerkes property into the observatory, up through the up the stairs. So you know, it's an interesting chase scene flick. If you're interested. Of course, the mount was built by Warner and Sweezy. It stands 43 feet. The mount is 50 tons. It's huge. Comes apart in segments, and the deck and RA axes they weigh 5 tons each, and the gear weighs 20 tons. And of course, the telescope itself is 63 feet long and weighs 6 tons. Of course, the lenses are mounted. There are two of them. It's an achromatic doublet, crown lens, and a flint, and they weigh about 200 pounds. And so 200 pounds and 300, so 500 pounds of flint. The flint lens is the second lens, and the crown is the first. So they actually counter for dispersion. There's a picture of it in 1896. No lens is installed yet. And of course, this is what it looks like. Looks like today. The actual floor. So the floor is 75 feet in diameter. The floor itself is 37.5 tons. Now, the reason is that when the scope, when the objective lens of the scope drops, you see a target more towards the horizon. What happens, right? The end rises. So how are you going to use the optical end of the scope if the objective is actually dropping? So they had this ladder, this stool ladder, but what actually happens is the floor rises. It rises up 23 feet. All right. So in order for the floor to rise, they had these 4 of the counterweight stations, right, to actually help raise and lower this 37.5 ton floor. And of course, the stations are 6 tons each. All right. So here's a picture of 1896, 40-inch being the mountain actually being built. So what's underneath is this supports the mount. So this structure is on the underside of the floor and supports the weight, all this weight. The dynamo DC motor here, which provides the mount power, and I believe it's still the original dynamo. And I heard it said it's Edison's dynamo. I'm not sure if that.
Those big wheels to rotate it by hand.
Big wheels, these,
Yeah.
that's the RA deck. Right ascension deck. So, you know, you can see the numbers.
Oh, it's the scale.
Yeah.
The angle.
Versus this is looking down through the slit at the mount. All right, so the 40-inch lenses, the actual lenses were actually installed on May 20th, 1897. The first flight was the very next day, May 21st. And of course, Barnard and Hale were so excited, you know, gotta look through this. So they're actually testing it. They looked at the Ring Nebula, the Dumbbell, and the Hercules star clusters. And the evening of May 28th, Barnard was working late, finished around 1 o'clock in the morning. He lived right next door to the observatory, had a house. So he went home. And then for maintenance the very next day, they actually raised the floor. So the floor right now, look size of the mount. So here's the mount, right? So here's the floor. And of course the highest point the floor rises is right here. So it's right here. Right. What had happened then, about 3 o'clock in the morning, the floor collapsed. It fell into the basement. Pictures of it. So it actually fell, one side fell. Here's the upper end on one side of the floor, and the other side is down on this end. Right. Imagine what would happen if you were actually working on the floor now collapses. What would happen is one of the 1-inch cables of those weights actually broke, which then caused the floor to drop, which actually then caused a three month delay in the opening. Here's the offending cable, 1-inch cable. Of course, it was totally redesigned, delayed for 60 days, cost $5,000, which in today's dollars is about $200,000 in repair. And of course, this is the floor counterweights. And this is still there today, still used today. So everything's like, except the cables are much better designed, attached better. Here's the opening dedication. 1897, 2 domes. Third dome is not yet. Southeast dome, still not there yet. Yerkes is not here. He's in London, working on the Underground Railroad. But that's a dedication group. And of course, Yerkes is famous for the amount of work that happened at Yerkes, as well as the astrophysicists and physicists that were there. Here's a famous picture I'm sure you've seen, May 6, 1921, Albert Einstein. I really like this photo, a little of others, because this is the original. In fact, someone had to write down folks' names. I actually wrote them on the photograph, on photograph. Actually records who was actually there. Hubble got his PhD work at Yerkes. Famous for proposing the version of the universe expansion. Ritchie, sure we've heard a lot about Ritchie, Albert Einstein, of course. Frank Ross, I'll talk about a little bit about Frank. And total recovery. He succeeded Barnard. He came from Kodak. And he developed the wide angle lenses at Kodak. Roman, she was the first NASA chief of astronomy. Kuiper, people heard about Kuiper Belt. He was the director twice, father of planetary science. And Carl Sagan was a student of Kuiper. Carl got his PhD at Yerkes. And of course, Chandra. Chandra is probably one of the latest notables. He won the Nobel Prize in 1983 for structure of stars and the Chandra limit. Chandra limit is determining whether a star is going to go supernova. I think at the time it was like 2.5 times the density of our sun, which I think has now been disproven. But anyway, that was what the Chandra limit was. Picture of 1932. The instrumentation, of course, big handles. And I like the binder scope of the 40-inch. These are the other scopes. This is a 41-inch. We always call it the 41-inch because it's really a 41, even though it says that it's a 40. This is the one that we had used. We barely ever used the 40-inch. It's 41 is what we did all our work on, because it had an optical tube that went down into the basement, and we actually Dr. Walter Wild, who actually created our group, he was one of the early developers of what we take for granted today as adaptive optics. And Yerkes was one of the primary places where the original adaptive optics work was actually done. This is the laser bench in the basement. We used to shoot a laser up the tube, out the telescope, across Lake Geneva. Of course, as soon as we did that, the police station gets all kinds of calls, and we're being invaded by aliens, and what's going on. But anyway, that's how they used to test the adaptive optics, by shooting a laser across Lake Geneva. Of course, so most times you could barely see it. It was just when it got really foggy, then you could see it, but otherwise, no one would ever see it. These are the judge's instrumentation, like all good labs. Total mess. This is the other scope, 24-inch. At the time that we were there, we were refurbishing it. I spent a lot of time fixing the mirrors. But in this particular picture, it looks like they've really done a good job refurbishing it. Other items of note, this is the original library in 1897. This is now what it looks like today. Bust of Yerkes. This is Yerkes Observatory stats. And normally you think, okay, so what? What's amazing about these stats is that you could spend hours just looking what is on each stack. The amount of history that is housed here, as well as the early calculating machines used by the human computers, being women at the time, they were called computers. These special machines are actually built for early astronomical work and calculations. They don't exist anywhere else in the world except for sitting on these shelves and these stacks. And my wife Linda asked, the tours go right through here. And so aren't you concerned about people stealing, like just lifting something? I said, no, the small tours, they pretty much know what, they haven't experienced any kind of theft or but it's truly amazing what is in these stacks. I mean, Sagan's PhD thesis is one of the stacks. In fact, I spent some time looking through it. This is in the library, and it's a big sphere. It's a big sphere, and Kuiper and Sagan actually overlaid moon maps on this, and that's how they determined the Apollo landing sites. Was by overlaying pictures of the moon on this sphere, and they actually would determine where Apollo should be landing. That's still in the library. Okay, Pluto. We all know it's discovered by Clyde Tombaugh in 1930, based upon some pictures he took in January. And they declared that they found Pluto February 18th. He used a blink comparator. Here's a picture of it, sort of in front of it at least. And as I think most of you know, blink comparator is just comparing photographic plates and then blinking between them to see if anything moves, right? And that's, but the problem in doing that is that you're looking at, you know, anywhere from 50,000 to 900,000 stars. Is extremely tedious task of looking at these plates. And Pluto at the time was 15th magnitude, very, very dim. Now Pluto's name, interesting enough, once they discovered it, actually was named by Venetia Fair, who was schoolgirl in London. And she named it Pluto because she was discovering, she was actually studying classical, I forget the term now, but anyway, she actually named it. It's a friend of a friend to Percy Lowell that they decided. Plus, PL Pluto was initials for Percy Lowell, which I thought, hey, great. We're just going to name it Pluto, and this was the original symbol with P with that. No longer used today, but that was the original symbol for Pluto. Okay, Pluto is very interesting. It is, for one thing, is its orbit, 248 years. And if you look back, you know, what happened today 248 years ago, right? Well, we were in the middle of the Revolutionary War, right? George Washington, and George is probably just off the street here, right? So 248 years, a long time. Mean distance, 3.7 billion miles. And what's interesting about Pluto is that it's not in the same plane as the other planets in the solar system, right? It's actually a 17 degree inclination. So it's actually coming up and going back down through the solar system's ecliptic plane. From the time that it was discovered and we actually see it, it's observed orbit. In other words, visual observations are only 38% of its orbit. Now I'll discuss a little bit why that's important. Has 5 satellites: Charon, Nix, Hydra, Styx, and Kerberos. What's interesting is that Pluto's diameter is only 1,500 miles wide, and Charon, its moon, its big moon, is 750 miles. Now, what's important about that is that they are a mutual tidal lock. So what does that mean? Our moon is in a tidal lock with the Earth, right? So we only see one side of the moon. In this case, Pluto and Charon are both mutually in tidal lock. So both sides, both faces of Pluto and Charon only see each other at all times. Even though then this system rotates, its day is basically six of our days, right? So this whole system is rotating, but they're in mutual tidal quite a lot. And of course, the center of mass between these two is 700 miles, about 700 miles above Pluto's surface. Yes, sir.
Uh, how does the distance between the two vary?
I don't know. Actually, I don't. That's a good question. I don't know. I don't think it varies very, very much. But like all systems, right? It would vary. But I don't know. They are 12,000 miles apart. So, probably obviously some movement. It is believed that Sharon was part of Pluto. That came out of the New Horizons when it zoomed by. And of course it has nitrogen glaciers, oceans, it's all nitrogen. However, it is believed at the New Horizons, they believe that right below the surface is ocean water. A great deal of water is on Pluto with a silica core. Of course, the surface temperature ranges from -400 to -360 degrees Fahrenheit. Balmy -360. It is very, very, very cold. It's also believed nitrogen atmosphere would freeze and fall to the surface as the Pluto got away from the sun. New Horizons show that is not true. So what was really believed to be true, New Horizons had shown otherwise. What is also interesting between these two, it's 12,000 miles apart, material actually flows back and forth, which I find really interesting. Surface material actually flows back and forth to Sharon and that's Pluto. How that actually physically happens, I don't know, but I find that extremely interesting. There's a picture of Pluto and Sharon, taken July 12th, 2015 by New Horizons. It's 1.6 million miles, 2 days away from its coastal approach. This was taken because as soon as you give it a 90 days of the target, JPL goes to optical navigation. And so the picture was taken due to optical navigation. Okay, the demotion of Pluto. We all love Pluto. Why is it not a planet? All right. We have our good friend, Dr. Neil Tyson, who led the way. And he's very vocal about, yes, I got rid of Pluto as a planet. And he's very vocal about that. He started by when they did a new solar system exhibit at the Hayden Planetarium. And when they did the exhibit, Pluto was not part of the exhibit. People went, "Where's Pluto?" And of course the answer is, well, Pluto's up for debate about being a planet. All right, so then what happened in January 2005, what really did it was a trans-Neptune object called Eris was discovered. Eris ended up to be more massive, dense than Pluto. Even though Pluto was larger, Eris was denser. And so the whole question came up about, well, then what is a planet? Now I'd be surprised that Eris was never found before. I find that amazing, but it wasn't found until 2005 with Caltech at Palomar. So the mass is 20% larger than greater than Pluto. As I said, Pluto's larger. So then what happened in August 2006 was the International Astronomical Union had a meeting and they came up with 3 criteria, right? To be a planet, you must orbit the sun. To be a planet, you must be massive enough to be rounded by its own gravity. And it must clear its orbit, right? Pluto doesn't clear its orbit. In fact, it comes back into the Kuiper belt on its orbit, and it doesn't clear it. In other words, it's actually running into things, and it's not large enough to be able to pull material in. and eventually clear out its orbit. It fails on this point. So does Eris. Eris fails on this point as well. And so that's why, however, Pluto is now an example of what a dwarf planet is. So resolution is 6A. Pluto is a dwarf planet and creates this category called trans-Neptunian object. Okay, so that's why Pluto is no longer with us. And I've done something here. As I said, Pluto and Eris. Eris comes back into the Kuiper. Pluto is outside the Kuiper, but then comes back in. He's actually is almost onto the Neptune's orbit. At one point, it's just another picture. This is Pluto's 17-degree inclination. It goes below the ecliptic, above the ecliptic. In fact, when Clyde discovered Pluto, he actually discovered it as it was coming up through the ecliptic. If it wasn't at the ecliptic, it's not likely he would have ever seen it. So it's almost a sheer chance that he actually saw it, because it was passing right through the ecliptic. Here's New Horizons coming out of the Kuiper belt now. Here's Voyager 2, Pioneer 10, Pioneer 11, and Voyager 1. All, of course, leaving my solar system. Okay, Pluto. Picture Barnard. He's the one who took the majority of the photographic plates we're talking about. He was actually looking for Halley's Comet. And I'll show you why we think that and why we know that. This is off of Yerkes' website. Just copied it. They actually show where Pluto is amongst the asteroids. I'm not sure where they got this from. I think I would have used this, but Pluto's there, and of course they say it's the first ever photograph Pluto. This is Barnard's observatory for the Bruce telescope that he had used. It's a separate scope, so they built a separate housing for it. See Lake Geneva over here. And this is a photograph of 1904. Right.
Is that the same Bruce that funded by the same Bruce that funded a telescope for Harvard?
Yes.
That's out there.
Yeah. I think so, yes. Okay, the pre-covering. How much time do I have? Okay.
Much fun to do.
Oh, all right.
We will go to what?
Okay. Our group was called the Assay Group for Asteroid Search Science by amateurs at Yerkes. And so we existed from 97 to 2018, albeit the majority of our work was up to the year 2000. Dr. Walter Wild had formed our group. The physicist, he was an astrophysicist, he spent a great deal of his time in adaptive optics. He was out of the University of Chicago. He did much of the waterfront control experiments. He actually convinced NASA to get it was destined for the space shuttle. He convinced them they'd be much better at Yerkes than on the space shuttle. And so they agreed. He also did a great deal of work on rigging Star Wars, which actually led to his work actually ended up on the Webb telescope. But what assay was meant to do, in the 41-inch scope, we were actually to come up with algorithms and come up with means which to find near-Earth objects, nails. Because there's a great deal of concern even back in 1996, 1997, about objects that we can't see that are approaching Earth, asteroids, other large meteors. And what typically happens is you don't see them until after they pass through the Earth. Obviously, it's too late. You can't see them coming at you. And so the goal was to develop algorithms and means and technology whereby you could more easily, at that time, more easily be able to find them. The assay group was comprised of amateurs, astronomy people with specialty skills. So we had myself out of Bell Laboratories in Chicago. We had folks out of Motorola. We had other folks from other skill sets, other walks of life. We have electrical engineering, systems engineering, software engineering, all different engineering skills, which then together form the assay group in which to accomplish these types of goals. Very, very tight group, but small. There's only about 5 or 6 of us. And so Walter led that group. These are the 2 of the plates. These are what the plates look like. Some of them were fairly large. And of course, we had an office there. This is the southeast and the northeast dome. The walls were curved, so when you stick a desk up against the desk, and there's a big gap.
The plates are curved,
Plates are curved.
are the plates curved?
No,
Oh.
the walls are curved. These walls are curved.
Looked at a picture, oh, curved. I guess.
So we use a stereo microscope. Here's a friend of mine, Greg, we're looking. So we'll talk about the plates a bit. Yeah, so the plates turn of the century plates. So they have photographic emulsion on them, which is a thin film and glass. Over time, the emulsion dries out and cracks, peels. It actually peels right off, right? Also, the silver halide, the silver material, the photographic material, the actual material itself was about 17th, 18th magnitude. So you actually can see the photographic halide material on the plates, which to find Pluto, right? The silver material is actually larger than Pluto itself, which causes more problems. So we had to deal with that. That's why the stereo microscope came in because you could see the emulsion, which had a regular pattern, and then anything else that didn't fit that regular pattern, that was an object of interest. Precoveries. These are the 2 precoveries that this finding was produced, August 20th and November 11th, 1909. Of course, they were both taken by Barnard. Frank Ross, which I already mentioned, he succeeded Barnard. He was there from 1874 to 1960. 1874 to 1960. He was looking for Pluto as well. And he found on a Barnard plate, I think in 1921, he found Pluto on this plate. And then Pluto actually appeared on a plate that he had taken. And he had taken that plate in 1927. Never knew he had Pluto, of course, but then went back and looked at his earlier material and he discovered, hey, I had Pluto. I never knew it. All right. So the pre-coverage of Pluto, Yerke says 1, 2, 3, that's 4. 4 cases. Of course, there's others. Harvard has 1. Heidelberg Observatory has 2. Mount Wilson, of course, has 4. Or 4 has 6.
Like, what are the white patches?
The white patches. These?
Yeah.
Oh, they're just stickies. The corner that's what our target, that's where Pluto is, so instead of marking the plate, which we don't wanna do. So we put stickies on the emulsion to actually, right in that corner is the target. However, Frank used a green pen, ink pen, fountain pen to actually mark on the plates. And we know it's him because on his notes, he used a green ink pen. And the same photographic plates that we were actually looking at, he actually marked on the emulsion with his green pen. So we actually know that it was Frank who was actually doing it. In fact, the two plates that we were actually used, he actually had markings on it. He had markings on the sleeves that plates were in. So he was actually looking at the same place. Just that he didn't have the tools that we had to actually locate it. Reason why we know, okay, so these are the two entries in Barnard's logbook. We had full access to all his logbooks and all his records. These are the two plates, 583 and 556. Gave the right ascension and declination that he was looking. Hours of exposure, 1 hour and 19 minutes on this one. His notes, his objective, Halley's Comet. So we know he was going after Halley's Comet. He's expecting it at some time, and he's trying to find it. He's trying to locate it.
And all these exposures were manually guided.
Oh, yes, yeah. They did have a clock. They had a conical clock, at least for the 440-inch. I'm not sure what he used for the Bruce. So I'm not sure how he actually guided. Okay. It's an important chart. And especially the next one. So these are pictures of the two plates, albeit they're blown up 6 times. All right, so but this is not the picture of the original plates, because we had enlarged them 6 times. And we had to reverse the color so that we could see the dark targets against a black background, white background. So this is 583. This is 556. Taking with a 6-inch Bruce and the plate 583. So he would take he had 6 inches, 6-inch 6-inch lens and a 10-inch. And so those were, so we had 10-inch plates and 6-inch plates. We talked about the emulsion. Another problem we had, plates are blue sensitive. Pluto is reddish due to its atmospheric chemistry, methane, carbon dioxide. I'm not sure about nitrogen, but Pluto has a reddish hue. So that's another problem. So blue sensitive plates, trying to find an object that is reddish hue, right? But anyway, on these two plates though, I know PowerPoint and copying is difficult. Look, there's a little smudge right here, which is Pluto. And of course, a little smudge is right there, is Pluto. The rest of these little dots you see all the way through here, that is the photographic emulsion. So you can see a little disturbance within the emulsion, right? And so that was the challenge. We did look through approximately 300 plates, 400 plates in that category, in order to find the right sets of plates. Okay, at that time, Pluto. Okay, so what was important were the asterisms. So how do you find something that's going to be a smudge? And so how do you find a smudge against these plates? And so the only thing you can go on is what are the asterisms like around your potential target? So this is a picture from the tool at the time was Metastar. which is a big software program used in the late nineties. So we look for these types of asterisms. These are asterisms around Pluto. Pluto was in retrograde. So November 12th and November 11th here, and of course August 20th, Pluto was here. But it's also within 17 minutes, right? So this field is 17 minutes for 27 in the constellation Taurus. All right. The likelihood of seeing Pluto at two different dates on the same plate is highly likely, given the size that we're looking at, right? So that becomes really, really, really key. And we didn't realize that. We actually realized that we're a couple of beers at local pub. We figured it was like, wait a minute, you know. So we actually, we had a eureka moment. So it's a 17-minute field. Right. So here's the evidence. All right. So one thing you got to keep in mind is asterisms. We have two plates, right? And the plates have the same sky field. Okay. So this is August 20th, November 11th. This is 6 feet 583, 556, August 20th, November 11th, and 583. Okay. So the asterisms are here. We got 3 stars, a couple of stars here. Smudge of Pluto is right there, right? Okay. On November 11th now, we had to prove, no, you couldn't say, well, yeah, it's a smudge here, and it must be Pluto. Sorry, doesn't fly, right? Even though you have software that says, well, yeah, software says it's there. We also used the 1949 National Geographic Survey, which was the largest survey at that time. We also used the National Geographic Survey. Yerkes was fortunate to have the plates. We can actually use that. But just saying that, you know, here's other evidence. It was still obviously in science, that's not good enough. We had to show that Pluto moved. I had to show that Pluto moved. So in November 11th, the same sky field, different plates. There's the same asterisms with 3 stars. Pluto's not there. The smudge was not there, right? Because it was over here on August 20th. November 11th, it was not there yet, right? Same on November 11th. Pluto moved. November 11th, it's now here on the 6B 583 plate, right? And if you look at November 11th, on this set of asterisms, it's not there, right? So it actually moved from August 20th out of this set, from this asterism to November 11th, in this asterism, all within the same 17-minute sky field. Okay. If I sufficiently confused you now? Okay. It even took us a long time to figure.
Do you do this visually to find these spiders?
Yes. Stereo microscope, and of course, with the aid of the 1949 National Sky Geographic Survey, as well as Metastar. At least determine where the asterisms are, and then using stereoscopic microscopes, we actually could. Yep, that's it. Now, what had happened, right? So again, there's the. Okay, I'll just move on. So the significance is okay. All right, a bunch of amateurs found this. Walter Wild was, of course, part of it. Walter Wild was extremely respected in the field. Walter says, "Yeah, we think we got it." People that listened, right? What had happened was this discovery, this recovery increased the observed orbit from 27% to 36% at that time. Right, today's 38%, but in 1999, we did this work in 97 and 98, concluded 99. This is extremely important. reason why it was important, the Pluto Kuiper Express is being planned by JPL and NASA. This is extremely important. The reason is that there's be two spacecraft. There's a two spacecraft flyby. And it was going to fly by so fast on Pluto that they sent two of them. One would take initial photos, and they needed the second one to follow up to take additional photos. So that's why two. But because there's two, Congress went, wait a minute, time out, too expensive. So that eventually led to the New Horizons, which was one spacecraft. However, JPL said, oh, wait a minute. Again, all our observation of Pluto is visual. All the ephemerides that we have, the solid ephemerides we have, is visual. The other ephemerides are derived mathematically, albeit good, but not great, because Pluto goes through the Kuiper belt and all kinds of things happen, gravitational fields and the like. Pluto may not be exactly where we think it should be on the flyby. And if it's not in the flyby, and at least not close enough for the observational navigation that would take place, we're going to spend too much fuel, and we may never even get there. This extended their calculations to improve the orbital and deep navigation for JPL. JPL confirmed the actual location of Pluto on those plates. There's some controversy about, well, Chicago didn't, and there's a lot of not invented here that went on, but anyway, JPL said, yeah, it stated that we are now we're not using. So at the time, they're going to fly by 11 miles per second, and altitude of 9,300 miles. Pretty fast, pretty close. Fuel was a big concern for course correction. Of course, now that the plates as of last month are now owned by Yerkes and the foundation. Up to that point, University of Chicago owned the plates, and as of last month, Yerkes now owns the plates. And of course, they have a whole strategy now in place to preserve that data and digitize it. Of course, they require funding, which should do that. Sure.
The 17-minute trajectory that you showed, if you were to extrapolate that, does it fit the orbit that now we know as Pluto orbit?
By and large, yeah.
Yeah.
Yeah. You mean the inclination? Yeah.
Another question. As part of this digitization, is there any possibility of normalizing the place, like taking out the silver element?
Yeah, I haven't seen the actual technique by which how they're doing it. Yeah, that would have to be, obviously that would have to be done. There are special techniques for these old plates, and I think that's part of the long process that it takes to actually do this. Plus, there's cracks and there's cracks in the emulsion, and maybe some of the actual pieces missing. And so I think it's a very laborious task to digitize these very old plates. And of course, it has to be a priority, right? Which ones do we need to digitize, and why do we need to digitize them? Of course, the goal is to look for comets. And so that's why the strategy is very important. Plus inventory. What is it that we have? 180,000 plates. How do you catalog this? And when we went through it manually trying to find this stuff, right? So we went through Barnard's notes, and we need this one and this one and this one. So then by pulling them out and looking at their envelope and the ID tag on the envelopes, that's how we actually would find them. But we went through hundreds and hundreds of these plates, right? Of course, we did it when the clouds were, when the night skies were bad and nothing else to do. So. Yerkes during the daytime, this is their website. Please visit their website. Plan a visit if you're in Wisconsin or Chicago, please. They offer tours and you can buy tickets online. If you want to buy 8 weeks in advance. But they host group tours. They also host weddings. Yeah. Private events, concerts. Here's a concert going on, and there's a tour. And they have quite an education center now there. And it's quite a spot. And they actually do real research work and of course not to the liking of during its heyday, but they're doing real work. Hey, any other questions? Yes, sir.
Given the movement of the floor, how do floors get in now?
I'm sorry.
Given that the floor goes up and down.
Oh, they don't raise the floor is kept at the same level at the front door is. And yeah, it's a good question. Because you couldn't exit, you couldn't leave, the floor was up above above your entry door or below it, right? The door's up, 10 feet up. So yeah, good question. As far as evacuation, like if you had to get out, yeah, I think that would have been a problem. I don't think they really thought through that. There is a helical stairs along the sides. You could go up to there's a walkway up above where the wheels are. But you could go up that way and come back down. But yeah, good question. Bob.
Is Barnard's discovery of the proper motions of the star called Barnard star vessel?
I wouldn't know that. You would probably be the expert on that, Bob.
I'll figure it out.
Yeah. Yeah. Thanks, Kim.
I have a comment. Don't know anything about planets. My 6-year-old grandson knows everything. I'm surprised. I'm just surprised that, it's a big deal to find a planet. I thought even if it's a non-planet, I thought you would look up and say, yeah, that's it right there. Saturn and Mars and Pluto. I'm just surprised that this is a big deal to find a planet. I thought, for 1,000 years, people have been looking at planets, just looking at the stars. But you're farther away, right? Both of them.
Well, the trans-Neptunian objects are difficult to see. Can't see those. And but you're right. I mean, like Eris was found in 2005, and I'm actually surprised it took so long to actually find it. But as the stuff gets into the Kuiper belt, it's very difficult to see anything within the Kuiper belt.
What is the Kuiper belt?
The Kuiper belt is a orbit of large material, much like the asteroid belt that we hear about. But the Kuiper belt is like the asteroid belt, except much wider. In fact, there's a Kuiper belt. The Kuiper belt is this large body circling our solar system. So it is a source of probably what formed our planets, and the planets sweep all that out, right? So at when the sun was first born, and the planets were not yet made up our solar system, this is likely what we look like. All this material, the planets formed from, if you will, the Kuiper belt, and then the planets cleared out their fields, cleared out their orbits. So now you don't see the Kuiper belt amongst the planets, but still exists way out here. Okay. So it's just a ring, same plane as planets, but a lot of the comets, rocks, ice, a lot of the dwarf planets now seem to be in there. It's estimated 100,000 objects be as wide, 62 miles wide object. And of course, then it gets even larger. We have the Oort cloud, right? And that cloud is actually encompasses spherically our solar system. And so here's our solar system here, and yet we have another cloud that's actually encompassing spherically around us, and that's called the Oort cloud.
So does that mean the dust particles, for lack of a better description, of the Kuiper belt is what our planets are made from?
Yeah.
And how they,
They condense by, they collapse through collision, then they form enough gravity whereby they become larger and larger, and then they start sucking in more and more. And then under their own gravity, they become round, thus becomes a planet, and then they become larger and they sweep around. Now, I think that's generally true. Jupiter, as an example, it's said that Jupiter was probably the sun and Jupiter could have been a binary star. And that Jupiter just failed. It actually fizzled out, never became a star. If you look at what the contents of Jupiter, it's a great deal of hydrogen. I think it's a great deal of hydrogen right now. So it is basically, it is a failed star. So it's not like, pretty much not like the rest of the planets being iron based, as we are up to Mars, and then Jupiter, Saturn, and the others become more like, very gaseous type planets. Just let's see other items of interest. This is the powerhouse, no longer there. That's where Yerkes got his power from. Had 2 dynamos, 200 amps, 125 volts, run by steam. Because they're doing observations, had to be smokeless. They had smokeless furnaces, which I thought was unique thinking. Got its water from a 165-foot well. And electrical cables and steam pipes ran from this powerhouse to the observatory. That's no longer there.
Is the region looking dark there now, or is it light pollution?
Light pollution. It's pretty, it's like Geneva. It's worse in the summer, of course, because all the vacationers out of Chicago and all the restaurants and everything's lit up. It's much better, like I said, it's much better in the winter when everyone's gone. And so it gets much darker in the winter. This is how it kept time with the conical engine, which can control the speed of rotation. This is some of the work of Sophia with the adaptive optics. This is the renovation. You see all the draped plastic to protect the. Here's the wheel that you asked about. And so
Who is that, like a quartz measurement?
that's there.
I'm
sorry.
You use that for something,
Just as location as to where the RA and deck is.
but it's not very accurate.
No, it's not that accurate. No, it's just visual. Comparison of the roof of the solar cells, what it looks like now versus back in the late 90s. No solar cells. That's the southeast dome. This is the dome, the 41-inch what it was in. This is shoot razors out of. That's where we did the nail work out of was the 41-inch, which is this dome here. This dome is hardly ever used because the scope is so bad, had to be refurbished, and the reflector plate was very bad. Someone left the dome open and it rained. The water got into the scope, and imagine what happens to the mirror. Accidents happen. Sir.
Did you said you have a meridian transit?
I'm sorry, I'm ready.
Did these ever have a meridian transit instrument?
I don't know. I don't know. I would imagine so, but I'm not aware of it or saw it. And two smaller domes on the property. 14-inch Cassegrain is in them, and then one's. So used for some minor work. All right, well, thank you very much.